So today we are happy to have a very distinguished speaker from Nordita, Professor Antti Niemi, who will give a talk on time-crystalline vortices, stagnation points, and Poincare Index Formula. So it's a pleasure to have you. Please, Antti.
Okay, thanks. So yeah, so this is some work that I have done over the or something related to this the last 2 years with Anton Alexeev, Chindai, Karaud, and Vilcek. So I'll give you first just some kind of a plan what I will do. First, I will tell you about the textbook results on on the subject that I will talk about, which is basically vortices in the Gross-Pitaevskii equation. Then I will go to the work that we have done. I will argue that vortices can be viewed as realizations of the so-called time crystal concept. I will then show how vortices, the statistical vortices in this Gross-Pitaevskii equation is a fractional, that is, they are examples of anyons. I will show how there are some phase transitions can be realized in the vortex system. And then I will conclude with trying to develop an order parameter for the phase transition, which is a topological. So it's has very elaborate, it has problems in with the order parameters. So what I will study is the equation that I will study is very simple. It is just this Gross-Pitaevskii equation. If you take these three terms, you recognize here a harmonic oscillator, Schroedinger equation for harmonic oscillator. And what I add to it is a nonlinear term, which is the quartic potential, and when I write the free energy. So it is essentially it is a nonlinear Schroedinger equation in 2 dimensions that I consider. It was shown in 1990s that this equation is closely connected to the phenomenon of Bose-Einstein condensation called alkaline atoms. And there was a substantial mathematical physics research on the properties of this equation and its discretization or its finite form. In particular, Elliott Leap and his collaborators wrote a series of papers where they showed that in the way how they understand rigor is that this equation does describe the ultra-cold Bose-Einstein condensation of alkaline atoms in a typical experimental situation when the number of atoms becomes large. So what are the known results that one has here? The interest in the equation is that it describes vortices. However, that the vortices, to get out the vortices, one needs to elaborate a little on the model, because if you just take the free energy and you try to find out the extreme of the free energy, you find an equation where all the 3 factors are positive definite. So the only solution would be a vanishing wave function. So there are no solutions whatsoever to the free static Gross-Pitaevskii equation, except just psi is identically 0. So what one does then is to take the system and rotate it. Rotating called Bose-Einstein condensates have been studied quite extensively in experimental physics. So if one takes this equation and puts it in a rotating frame, that is, rotates it with some angular velocity omega, then the free energy picks up at the constant angular velocity. Then the free energy picks up an additional term, and due to this additional term, the ensuing equation of motion is not anymore positive definite, but it turns out to have solutions that are non-trivial. You can also add a chemical potential there, so you get kind of an eigenvalue equation, if that's the way what you want to do. And what are the properties of these solutions? To reveal the solutions, one needs to do numerical simulations, and one finds out the following spectrum. Depending on the speed of rotation, you have different vortex solutions. If the rotation speed is slow, you have just the wave function, Gaussian wave function essentially, with no structure whatsoever. And for those values of the angular velocity, this is the lowest energy solution of the free energy solution of the system. However, there is also another solution corresponding to a single vortex, but it has an energy which is larger than the ground state. But when omega reaches a critical value, this one vortex solution becomes the one that has the lowest free energy, and so on, increasing the omega. You see stepwise 2, 3, 4, and so on vortices are the realizations of the lowest stationary point of the free energy. And why one got very excited about this, that one sees exactly the same kind of systems coming out in the cold atom Bose-Einstein condensate when you consider it in the rotating system. You find that the vortices form very regular abricosal lattices. So now I go, so this is what is basically the textbook result. And now I go beyond this textbook result to discuss the work that we have done. First of all, I will introduce what the concept of time crystal is and argue that the vortices can be viewed as realizations of the time crystals. So what is a time crystal? There are different definitions of the time crystal. And you can go to the Wikipedia to find out the definition. Actually, I took this definition or this kind of a statement what the time crystal is from Wikipedia around 3 years ago. Now it has again changed. There is not really, in the literature, there is not really very consistent agreement what time crystal is. For some people, everything that moves is a time crystal, but that's probably not very interesting subject. But what is true is that they were proposed in 2012 by Frank Wilczek as minimum energy structures of a physical system that, despite being minimum energy, is still in a motion. 2017, there were such systems were observed, but not in equilibrium system, in a driven non-equilibrium system. And since then, there has been a substantial, huge amount of research on the concept of time crystals, often in open systems that are out of equilibrium. Initially, Wilczek hoped that you could find the time crystals also in Hamiltonian systems, but there is an obvious problem. If you look for the Hamiltonian equations of motion for the momentum and the coordinate, and you want to look for the solution that would minimize the energy Hamiltonian. Well, the minimum energy is usually we identify the minimum energy as a critical point of the function of interest. But if you look for the critical points of the Hamiltonian, at the critical point, if it's a critical point, the derivative of Hamiltonian vanishes, but then Hamilton's equation says that also the time dependence of momentum and coordinate vanishes. So clearly, if you work at this level, you conclude that there cannot be any Hamiltonian systems where the lowest energy state would be time dependent. However, there is a caveat to this. Namely, suppose that I would consider just the Hamiltonian, for example, a harmonic oscillator. And for some reasons, I will then eventually describe why this is a natural way to look into the problem, is that there are some conditions. For example, if I take a harmonic oscillator and I take the condition that PQ has to be 1. Clearly now, if I ask what would be the minimum of the Hamiltonian, the minimum of the Hamiltonian cannot be the critical point, because the critical point would be P and Q is 0. But if P and Q is 0, P times Q cannot be 1. So if you then minimize this, you find that P and Q both equal 1, plus or minus, is the minimum value of the Hamiltonian function that it can get. And there is a very nice way to derive this result. Namely, if I look for the equivalent surfaces of the Hamiltonian, so it describes circles on the PQ plane, and if I look them at different radius, that is increasing the value of the energy, I realized that the point where it coincides with the condition is a point where the normals, where they are tangent to each other, that the normal of the gradient of the Hamiltonian and the gradient of the conditions coincide. That is, at the minimum value of the Hamiltonian subject to this condition, the gradient of the Hamiltonian is proportional to the gradient of the constraint. And if you work out this equation, you find the values that the minimum energies at P and Q is plus or minus 1. But you also find out what is the coefficient of proportionality that has the value 1. So there's a way how you can, in Hamiltonian systems, provided you have conditions, have minimum energy values that are not the critical points. And there's actually a theorem, the Lagrange multiplier theorem, that summarizes or generalizes this into very general Hamiltonian systems. That is, if I am interested in minimizing a Hamiltonian subject to some set of constraints, then the minimum of the Hamiltonian subject to this constraint is always a critical point of the Hamiltonian plus the constraint multiplied by Lagrange multipliers. So what you have here is an enough equal number of equations to solve for the critical point and for the Lagrange multipliers, and solving for the critical point of the Lagrange multipliers then constitutes the solution of interest. And basically my talk here will be just a realization of this Lagrange multiplier theorem in a certain content, that is of the Gross-Pitaevskii equation. So let me just summarize here. This is a talk that I usually give to physicists, so it's not very mathematical language, but those of you who work on symplectic geometry, I would say is that here I'm comparing two systems. This is a symplectic system and this is a pre-symplectic system. So going to these problems that I'm interested in, I go from symplectic geometry basically to pre-symplectic geometry. But let me talk it on a pedestrian way. So usually when we are looking for a physical system, so we have some energy and when we want to minimize this energy, as the physics education says, okay, let's look for the critical points, let's write the equations of motion and solve the equations. If you are interested in a critical point that would be time independent, you are out of luck because all the critical points of the Hamiltonian are time independent. So what instead, if you go to a more general system where you have the Hamiltonian, but then the Hamiltonian is subject to some conditions, then instead of trying to find the critical point of the Hamiltonian, you look for the critical point of Hamiltonian plus Lagrange multipliers multiplying the constraints. You find here you have introduced here n new degrees of freedom. You have n new equations. You have enough equations to solve not only for the critical point, but also for the conditions. And if it turns out that these Lagrange multipliers are not vanishing, then looking for the Hamiltonian equations, because the Hamiltonian equations is still the same as here, but dHdP, dHdQ can be written in terms of a Poisson bracket of the constraints times the Lagrange multipliers. If the Lagrange multipliers are non-vanishing, then the solution is time dependent. That is, you have a minimum energy configuration for the Hamiltonian system that is time dependent. That is, you have what one may call then a Hamiltonian time crystal. Usually these conditions are some, yes.
Let's say you're talking about quantum theory. Time crystals will have like a ground state.
Yeah.
So are we able to get that?
Well, it could be time dependent at the periodic or not. But, so I showed, we will show examples. So this is the general theory that we are trying to find, basically going from symplectic geometry to pre-symplectic geometry and looking for minimum energy configurations. So let's see what we can do in the contents of the Gross-Pitaevskii equation using this formalism. So the Gross-Pitaevskii equation, the time-dependent Gross-Pitaevskii equation is the critical point of the classical action that I had earlier. It has the psi star and psi, a complex variable. They have involve a linear derivative in the time. Those I can extract from this the Poisson bracket that psi star psi is 1. I have two conserved quantities that commute with the Hamiltonian. Those are the number operator and the angular momentum. And I can select the number operator. I can just use a normalization of the maybe the redefinition of coupling constant. I can choose the normalize with the number to 1. The angular momentum is then a free degree of freedom. So in addition of this Hamiltonian structure, I usually associate some kind of a topological structure here, and normally one associates to this the topological structure, which is the line integral of the phase of the complex field, which then computes the vorticity, computes the number of vortices eventually in the system. So I have here a Hamiltonian structure, and then I start to work on this using the Lagrange multiplier theorem. That is the question that I ask: can I have a minimum energy? Can I have configurations that minimize the free energy, subject to the condition that the number of particles is normalized to 1, and that the angular momentum has some value? This value of the angular momentum can basically be anything that is any real number, because this system here is now describes physically large number of condensed Bose-Einstein condensed atoms. So the angular momentum here is the angular momentum per particle. If the number of particles is very large, even if the angular momentum of the atoms is quantized, but if the number of particles is very large, then the angular momentum per particle in the limit of huge number of particles is essentially a continuous variable. Notice that there is no rotation here. So I'm thinking about a system where I deposit angular momentum to the system. You can do this, for example, by radiating with some polarized light, or using the Higgs-Kipler mechanism or something else. So it is physically feasible to consider system non-rotating system, and still carries some angular momentum. So now I have a setup for the Lagrange multiplier theorem. I have an objective function that I want to minimize, and it is subject to two conditions. That is, the objective function that I want to minimize is the energy function of the Gross-Pitaevskii equation plus Lagrange multiplier enforcing the number of particles to be 1, and another Lagrange multiplier enforcing the angular momentum to have its constant value. Recall that n and l are conserved quantities, so this is something that is preset in time. And then I've had the equations of motion instead of the critical points of the free energy. I now had this equation that gives that the gradient of the Hamiltonian is equals the gradient of the constraint contribution to the extended free energy, and I had the two conditions. And now I need to solve this and find that solution that minimizes the free energy of the Gross-Pitaevskii system. Obviously, this is quite a difficult, complex equation, but we have addressed it numerically. So the problem we have is then to find but what is important here is that to remind that if it turns out that for the solution the Lagrange multipliers are non-vanishing, then the solution of the Gross-Pitaevskii equation, the minimum energy solution, is time dependent. That is, I can write the Gross-Pitaevskii equation in terms of the Lagrange multipliers multiplying the field, because for the minimum energy configuration, the gradient of the Hamiltonian is equal to the gradient of the constant part. Thus, the minimum energy. I would have a minimum energy configuration with initial value, the minimizer, and then the time evolution defined by the Lagrange multipliers. Notice that it would be the minimum energy solution would be essentially symmetry transformation because it would be the gradients of the number of the conserved quantities. So we have my collaborator who knows how to do this. We has done extensive numerical simulation using some software where we have made attempts to locate the minimum energy minimizers of this problem. The methodology that we use is so-called augmented Lagrangian method, where instead of the constraints and Lagrange multipliers, we add an augmented term by quadratic function of the constraint minus the Lagrange multipliers, dressed with some parameters. And if you take the limit of the parameter going to infinity, you get it coincides with the origin. The minimum of this coincides with the minimum of the left-hand side. Just working it out and letting parameter go to infinity. So what we find is solutions that look like this. Here I will show you the evolution of the solution starting from the system where there is no angular momentum whatsoever, and then starting to increase the angular momentum. If here on the left-hand side, I have the modulus of the wave function, and on the right-hand side, I have the phase of the wave function. And you can see is that as the angular momentum increases, there is a vortex that starts moving from the boundary of the system towards the center. And once the one vortex solution has appeared, increasing further the angular momentum, a second vortex appears, and so on. By increasing the angular momentum, I get higher and higher vortex systems coming out. Initially, they are highly unsymmetric. They appear from some point on the boundary and then move towards close to the center of the system. So this is very, very different from the canonical approach to the Gross-Pitaevskii equation, where for small values of angular velocity, there are no vortices, and the vortices always make a symmetric arrangements. Arrangements. Here, the vortices, I have vortices for any value of angular momentum, and they depending on angular momentum, then they have different geometric arrangements. They do not form a Picasso lattices in general. Boundary conditions. Well, the boundary conditions. Yeah, the boundary conditions would be that you have a conserved current, that the flux of that there's no the number of the number is the density. You can define a conserved current where the number is the zeroth component of the current, and then it has a space component, which is basically Psi-Dacker deep psi. So the normal component of Psi-Dacker deep psi over the boundary on the boundary has to be zero. So there are no particles leaking out of the system. But the numerical yeah. This is the numerical simulations are on a disk. And if I take the circulation over the boundary, yeah, but that is no. Yeah, so we come to this. We come to this later when we start to look for this. Yeah. What is the? Yes. And they consider circulation over the boundary. Well, the circulation you get the circulation here. Here is the circulation is you take the gradient of the phase and you integrate it over a closed loop. So here I have. Maybe I could take this again. So you can compute the. We come to this. If you have a little, I will come to this. But yes, you have the circulation around the vortex is 1, and it is independently of how far you are from the vortex. Here I have one vortex, then I introduce another vortex. That is, it comes from basically, if this simulation would be all the way to the infinity, it would come basically from infinity. If I take any finite circle, at one point the vortex would come inside the circle, and there would be at that point a jump of the circulation, so that the circulation always counts the number of vortices, the net number of vortices inside the circle that you use for computing your circulation. Yeah, here, no, it is not fixed. It is not fixed because it depends. I mean, it jumps when a vortex goes through the boundary. The circulation is invariant only if the vector field is non-vanishing, but the vector field vanishes at the core of the vortex. So when the core of the vortex crosses your integration line, then of course there is a jump. But it jumps by integer because it goes through the zero of the vector field. So this is what we find. We find if I start, basically here I display a spectrum. In terms of the angular momentum, if I start from the value 0, and here I give the value 2, which was in the previous simulation, I find out that for very small values of the parameter L, there is a vortex that goes towards the center. Exactly at this point where the angular momentum is 1, it sits right at the center of the disk. That is then it coincides with the rotating system solution. But then when I increase the angular momentum, there is another vortex that enters the system, and so on. Increasing the angular momentum, I get more and more vortices appear in the system. And if I compute the Lagrange multipliers, I find out I have here displayed it for 3 different values of the coupling constant that are some kind of a generically but relevant for experimental systems. If you walk back the dimensional parameters, you see in particular that all the Lagrange multipliers are always non-vanishing. So that means that the systems, the solutions here, while I give you here a snapshot of the solution, the solutions are actually time dependent. They rotate around the system, they rotate around the center of the trap at the rate given by the values of the Lagrange multipliers. Yeah. Yeah.
And rotate to the center, right?
Yeah.
At the center. But now when I'm increasing the angular momentum, more vortices are coming, and they always like shift the other.
Let's see, we'll see. Maybe I'd have a next synthesis. So we come now to the analysis of the time dependence.
So they will form
No. They are abricos symmetric. They are abricos symmetric only here where you see a little jump on the or discontinuity in the first derivative of the. Yeah. No, this is not an integer. It happens to 0.1.8. This is at 1, but here the second abricosal is just at the point where the third vortex comes. There is a jump on the Lagrange multipliers in the discontinuity derivative of the Lagrange multipliers, and at that point I have a abricosal. Yeah, but it is rotating. It is rotating around the center of the trap.
So for simple vortex, how does it know that angular momentum is 1? What is 1?
The angular momentum 1 is the only vortex that sits, only system where the vortex sits right at the center of the trap. So it doesn't, you see no motion because the motion is basically rotational motion. For that, you don't observe any kind of a rotational motion. It just sits on the trap, but it evolves, its face rotates. So let me go to this time evolution because that is what basically your questions are addressing. So I will now argue that these vortices that I have here are actually anyons. That is, they are time dependent, but if I exchange 2 vortices, I find out that the relative phase doesn't change by a multiple of 2 pi. That would mean a boson, or multiplet of odd multiplet of pi, that would mean that they are fermions. But there is an arbitrary change in the relative phase. Those they are examples of anyons. That is two-dimensional. That is identical particles in 2 dimensions, where when you exchange them, you pick up a phase that is different from the phase you expect from a fermionic or a bosonic particle. Yeah. Yeah. Yeah.
I think it's at least in a linear system, which is not.
It's yeah. Yeah.
So the motion of the vortices, if the number more than 3,
well, yeah, yes, but it is, well, there is a, this is, well, let me say is that the Gross-Pitaevskii equation, if you use the Hashimoto transformation, you can write it in a Eulerian liquid realization. But unlike in an Euler fluid, where the vortices move because of the localized induction approximation, here they also move, but here the vortices are not singular like they are in the Eulerian function. They have a finite energy. So it is a little different. But, yeah. Yeah. But well, the point is that yeah. 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 Well, and that is not quite correct, because there's one important thing that you lack in the Euler function. Here I'm minimizing the free energy. In the case of an Euler function, you cannot minimize the free energy because it's infinite. So there's one ingredient that you have here that makes the difference, because I'm minimizing the free energy. If you would have a free energy in the Euler case, you would meaningfully be able to ask, how would the vortices move if they minimize the free energy? But the vortices have infinite energy. Yeah. No, not chaotic. And they have finite energy. So, but this is closely related to Euler fluids. I mean, if you think about Hashimoto transformation, that basically takes the wave function, combines the modulus of the wave function of the density of the fluid and the phase of the wave function as the integral of the velocity. Then, if you substitute it in the free energy, you get energy function that is closely related to the energy function that you would have of Euler fluids. But this is a very fluid dynamical system in a way. Because I'll show you. Yeah, because it's a minimum energy. It's a minimum energy, and I have conservation laws. So I have the conservation laws of the angular momentum and the number, but it's not integrable. It's not integrable. If I would increase the energy, I would not look for the minimum of the energy. Then it could be chaotic. But how I know that it's, I give you, it's a good question. But I'll give you. Yes, but let me show why I know that it cannot be chaotic. Here I have basically a proof that it's not chaotic, because the time evolution is a symmetry transformation. The time evolution, when the time evolution can be given, it is the derivative, if the symplectic gradient of the Hamiltonian, but the symplectic gradient of the Hamiltonian equals the gradient of the constant quantities. And so I can write the time evolution as a symmetry transformation. Then it cannot be chaotic. But that's an interesting point. Thanks for pointing this out. But it's an important, interesting point. So let me now go and show that this what happens when I look. Yeah.
So this is non
yeah.
I mean, you have just two motional integrals.
Yeah.
Momentum
yeah.
And momentum.
Yeah.
And but the system is non-integral.
Yeah.
But the way that the stochasticity is not right, because you can find this.
The minimum energy it's a minimum. If I would go in higher energy structures, yeah, I cannot argue that it would be non-chaotic. That I cannot argue. That I cannot. I have no comments on that. I haven't studied it, but I would have no argument to claim that it's a symmetry transformation. But yeah, Yeah. Then it would be more complicated. So, but let's now show that. Look at the time evolution. Here is the equation of motion for the minimum energy configuration. So the time evolution is Lagrange multiplier multiplying the wave function and its curve. Now I can combine these two terms in a single term that I have written here, that is P is ID slash, multiplied by where essentially I have a kind of a gauge field appearing. And this gauge field is the gradient of the phase of the angular coordinate, it's gradient of the phase on the plane, multiplied by a parameter, which is the ratio of the two Lagrange multiplier. And if I have this time evolution that I have, this is exactly the time evolution that, for example, Wilczek in his paper wrote, that would be followed by an anyon. That is there would be a statistical gauge field that would make the system to behave in such a way that when you exchange two vortices, you would get a phase that is not multiple of pi. So here I have first. Here I will show first a movie of one single axis vortex, and you can look at the phase here. Here is the location of the vortex, the vanishing of the modulus, and here you see the phase. When it goes around, you find out that the phase doesn't appear on the same place. That is, it goes around the center, and it accumulates a phase that is not the multiple of pi. And here in the second system, I'm now having the particular configuration where the two vortices are symmetrically located with respect to the center of the trap. And starting from this position, letting it the time evolve, I will find out the phase will not come back to itself multiple of pi. You see here that the phase will be different than a multiple of pi. It is the hallmark of anionic exchange. I'm exchanging two identical vortices here, and I find out that the common wave function picks up a phase that can be evaluated by evaluating the ratio of the two wave functions. So in this case, this is so to say, one could say what is the textbook example of how one would expect an anyon to behave. So the vortices here are not only minima of the system, but the minima are anionic in their exchange statistics. So now I come to the part of the talk where I think that I will have answers to Pasha's questions about the topology and so on. Namely, let me now look at analyze the topology or the topology of these structures and bring up some new structure here maybe. So conventionally, when we have a superfluids or Euler fluids or so on, we can have vortices that rotate clockwise and anti-vortices that rotate anti-clockwise. That is, we have structures with opposite circulation, so that the total circulation, if I go around the system, would be 0. And I can detect the presence of vortices and presence of anti-vortices by evaluating the circulation. If I take the circulation around the anti-vortex, I would get the -1. If I would take complete the circulation around the vortex, orienting the circulation in a clockwise way, I would get +1. And the total circulation would then vanish. And normally, in the case of superfluids, this is the only topological invariant that one associates to the system. But the question is, do we have some additional structure now in this explicit model of the Gross-Pitaevskii equation? And yes, we do have an additional structure that I will now analyze. Namely, what I can have is that I can have flows where I would have, for example, a vortex or an anti-vortex, but where the circulation is 1. But I can also have a saddle points, stagnation points. Those are points where the velocity of the fluid vanishes. And if I would calculate the circulation around the stagnation points, I would find out that that would have the structure of a saddle point. For those, even if they appear to be topologically specific points, the circulation for these points would be 0. You can form a vortex and a stagnation point pairwise. The total circulation is 0. The circulation here is 1. The circulation here is 0. The circulation changes because I have a 0 of the vector field when I had the bifurcation of a vortex saddle point formation. But then, in addition of the circulation, I can also introduce a winding number. Probably not Brouwer degree, I think, is the proper mathematical way, which is the quantity that I have here. The winding number you see is the numerator and denominator is even in the velocity field. Thus, it cannot make any difference between vortex or anti-vortex. Vortex and anti-vortex differ by a different sign of the vector field. But if I have something that is even on the vector field, it cannot be detected. However, the winding number would be able to detect the saddle. If I evaluate this winding number around a saddle point, I would find a value -1. So these are the two kind of a topological integral invariants that I want to associate for this system, and I want to see how they describe what I have. So let me now just look for this winding number and show how they differ for vortices and for saddle points. Here I take the winding number and I rotate. I have some initial vector field, which is vector field is -yx, and I rotate the vectors. And this is a continuous transformation. It is a continuous transformation. It cannot change the value of the winding number because the winding number is a topological invariant. But I see is that in the case of vortices and anti-vortices, clearly I have a vortex, then I have a star, then I have anti-vortex, and the value of the integral invariant doesn't change. But if I have a saddle point, the saddle point cannot be continuously deformed in any of these other topological structures. For saddle point is separated from all the other vortices and anti-vortices by this integral invariant. And saddle point is the only fixed point, so to say, where the winding number have number value -1. So do I see any value? Do I see this kind of a structures in the Gross-Pitaevskii equation? And can I have any value by analyzing it using these two integral invariants? Well, first of all, if I look for the vortex structures that I have, and I look for the vector fields in the case of a one vortex, I just see the velocity field circulating the vortex. I don't see any saddle point here. But if I introduce another vortex, what I find that it is not that this vortex would come by itself into the system. It comes into the system accompanied by a saddle point. If I introduce another vortex to the system, that also enters the system accompanied by a saddle point. And when the vortices come to the abrikoso kind of structures, the saddle points all move and aggregate in the center of the system. That is, I find out that except for the first vortex, all the additional vortices are, when they enter the system, they always come together with the saddle point. And interestingly, the saddle point, while the vortices stay around the center of the trap, the saddle point seem to move and aggregate, sit on top of each other at the center of the trap. However, if I continue this, introducing vortices here, I find out that well, if I have a 5, 4, 6 vortices, yes, again, the vortices come and aggregate to form apricot lattices, but the saddle points all aggregate to the center of the trap. However, around 6, 7, there's a transition. Instead of aggregating at the saddle point starts to move away from the center and form pairs with the vortices. And so when angular momentum becomes large enough, that increases, there is a transition in the topological arrangement of the saddle points. Instead of aggregating the saddle points, form pairs with the vortices and arrange into apricot type systems. Well, this is very, very similar to what one has in the Kosterlitz-Thouless transition in the XY model. Because in the XY model, if I have a large temperature, small beta is the inverse temperature. If I have a large temperature, I find out that I have a random, I have a aggregation. I don't have any clear assignment between vortices and saddle points. Saddle points, they are kind of randomly distributed. But if I lower the temperature, I find out that the saddle points and vortices in the XY model, the saddle points are the anti-vortices in that content, start to form pairs. So I have exactly the same kind of a transition here in the Gross-Pitaevskii model that I have in the Kosterlitz-Thouless model. That is, high temperature corresponds to small angular momentum, low temperature corresponds to large angular momentum, and there is a kind of what one can correctly state is a topological phase transitions, where the aggregation of the saddle points becomes broken, and the saddle points and the vortices become paired. This is also different from the Kosterlitz-Thouless model, because there the energy of the vortices and saddles is logarithmically divergent. Here everything is finite, and I'm looking for the minimum energy configuration. So this you can then analyze. You can try to analyze topological transitions. Phase transitions are notoriously difficult to analyze because they, first of all, they are not sharp phase transitions like normal phase transitions. They don't occur at a given temperature. They are kind of transitions, and one can prove their existence by looking only at very low temperatures, very large temperatures, and showing that they are different phases. And there's no order parameter, so to say. But here, so the order parameter one can try to develop, and I'm coming now to the end of my talk by just suggesting how to develop order parameters here. And it could be that the order parameters that one could use is the local structures of a combination of the winding number and the circulation. Namely, I have here find that they are I have found that there's I have introduced the winding number as an additional topological character of the vortex structures, and it turns out that the winding number it defines the index of the vector field. It can be computed in terms of the topology of the system. That is, it equals the Euler character plus half. If I compute this winding number around a closed trajectory on my disk or on my domain, the winding number equals the winding number describes the topology inside that trajectory and says that the topology is equal to the Euler number of the system plus half the number of internal and external trajectories. And this relation here is not the Poincare index, it's called the Poincare Index Formula. Slight difference from the it's different from the circulation. See, here the internal and external trajectories, this internal and external tangencies is defined so that if you look for an arbitrary trajectory that surrounds your topological system, so if you look at the tangents of this trajectory, if the tangent is internal to this domain, it is an internal trajectory. If it's external, it is an external trajectory. There are points where an internal trajectory changes into an external trajectory, and depending on how many continuous regions you have here, that counts where the tangent is internal. That gives you the integer for the internal trajectories, and then the number of segments where the tangent is external gives you an integer that I call the external tangencies. And this is an invariant that is computed by this winding number for an arbitrary trajectory. And previously, when I showed the spectrum of my systems, I pointed out that in the case of a single vortex, I find no saddle points whatsoever. In the case of two vortices, I find a one vortex. Three, I find a two vortices. That is consistent with the fact that for the disk, the Euler number is 1. So this is more or less where I had to give up on trying to do I have not proceeded beyond this, where I try to introduce topological quantities to characterize or play the role of order parameter in describing this phase transition that appears to be here. So I then come to the conclusions. And the lessons that I can draw from this analysis is that in physics we are always programmed to minimize the free energy by looking for its critical points. That is, we are programmed to look for the equations of motion. But the free energy minima in general, are not critical points of the free energy. In systems where you have conditions, you have to look more widely at the system in order to locate the free energy. Basically, this is that whenever you have a symplectic geometry, yes, then you can look for critical points of the Hamiltonian energy. But in the case of a pre-symplectic geometry, that is often the proper geometric framework. If you have conditions or constraint, you cannot proceed that way to locate the energy minimizers. And in Hamiltonian systems, when the critical points are not, the energy minimizers are not critical points, then in general they are time dependent. That is the realizations of time crystalline dynamics. And commonly, the conditions, unless they are constraints, they are commonly symmetry transformations. Constraints, of course, first-class constraints are also symmetry transformations. Due to the structure of the equation of the Lagrange multiplier equation, these these trajectories are then symmetry transformations. Because they are symmetry transformations, they cannot be chaotic. They are regular trajectories. They describe how a symmetry of the system. And it seems that in the case of a Gross-Pitaevskii equation, one finds new physical phenomena. I have shown that they are so energy minimizers have an anyonic statistics, and they are time crystals, and there also seems to be topological phase transitions that occur in these systems when you look for them for larger and larger values of the conserved quantities. And I have also shown how the Poincare Index Formula can be introduced here to try to identify the saddle point structures and to reveal the phase structure of the system. So possible it could be that when one looks for order parameters for systems that have topological phase transitions, it could be good to look for this kind of topological invariance more generally than the circulation. In this case, both the circulation and winding number can be used in tandem to look for the topological phase transition. And of course, generalization of this to three-dimensional systems and other models would be of an interesting subject of study. Okay, thank you.
Okay. Any questions?
If you have ordinary complex scalar field, we don't think about sellers.
Pardon?
We don't think of sellers. Suppose I have some complex scalar field, phase boson, and some condensation, then we don't think of sellers. Why is that?
Well, people haven't studied the saddles. I don't know. They have never. Well, it is a zero of the. It is I call them stagnation points because if you look for how do I get back? Now I simply have got stuck. Okay. I mean, how do you see them? Oh, it got stuck. Okay. No, okay. Okay. Yeah. So you see here. I mean, you can. But if you look for the saddle points, so here I have plotted the vector field, which is the velocity. It's the superfluid velocity. So around the vortex, the superfluid velocity circulates, and it becomes faster and faster. But on the stagnation points that I have here between two vortices, I have a stagnation point. At that point, if I would put some kind of atoms, for example, that would have a color or something like that, so that I can follow them, here they would not move. That would be a point where they just stop. So those are not been studied so much. They are not so easy to detect at vortices. I suppose that's the question. That's one of the reasons. But yes, they have their own interest in topology, and this topology is very can lead to phase structures. But yes, they have not been. I have not seen any literature where they have been. Well, why not? They are interesting. Now it, yeah, here, this one.
No, the last slide.
The last slide. Yeah, I had this. Now, this one.
Yes.
Yeah, it's the Poincare Index Formula.
Yeah, the left-hand side, I understand.
Yeah.
The middle is a name.
Yeah, it's a name.
What is done?
The right-hand side, this is the Euler character of the system. So for example, if I look for a disk, the Euler character is 1. If I can look for the two-dimensional manifold. Yes, this is a two-dimensional. It is a two-dimensional. I can have a vector fields on a torus and so more complex. The gamma is the gamma denotes the trajectory, because the index depends on the trajectory that you use. If I have here a trajectory that, for example, here, then there's nothing inside the trajectory, the index would be 0. But if I have, for example, here an index, I would detect one vortex. If I would make around here, I should get, if I look very carefully at the index, I should find out that the value of this integral is 4, because there are 5 vortices and the number of vortices minus stagnation points is 1. It depends depending on the trajectory, but if I take the trajectory like this, very close to the vortices, I would expect to have 4, and I would compute that contribution here by looking this trajectory that I have here. The trajectory could be complicated. I would look for the trajectory, how many internal and external tangencies I have there, and that would be then an invariant. That would be able to, I would be able to compute. Pardon? This line, it's a tangency. It's a tangent. So it's in this case, it's an internal tangent at this point. And here it has an external tangent.
So they match.
Well, the number of internal tangencies minus the external tangencies is the same as the index that I compute here minus the Euler character.
You have two-dimensional manifold
Yeah.
in this case.
Yeah.
if you have a vector field V, we choose a one-dimensional sphere.
Yeah. Circle. Yeah.
Which is called gamma.
Yeah.
Gamma is a manifold.
Yeah, it is. Yeah.
What is gamma?
It's a trajectory.
It's a one-dimensional.
It's a trajectory. It's a
Okay,
trajectory.
S1.
Yeah.
Okay, you choose. So
Yeah.
two-dimensional manifold.
Yeah, it's an S1. It's a deformed circle. It's an S1.
Yeah. Then you choose S1.
Yeah.
There is a vector field.
Yeah. Yeah, it is a vector field. Yes.
And this data, chi is
Euler character. It's for a disk.
two-dimensional manifold.
Yeah, because it's it's of the two dimensions. Yeah.
Depends on gamma.
Yeah. It's a well. If
It's characteristic of gamma, but it's
Yeah.
not dependent on gamma.
it's a yeah. Yeah,
And then,
that's probably
And
correct.
then there are two systems.
Yeah. Yeah. Okay. Yeah. It's yeah. That is yeah.
Yeah, okay, maybe one more precision. When the anyons and the vortices are coming, like you said, with the standard vortex saddle pairs, there's symmetric configurations that form like abricose lattices, like you mentioned, right? So this picture was good before.
This picture.
Yeah, like you see this, like you said, but developing this configuration of saddles, if in the first picture they like accumulate, the more you add, then they start to spread and form new symmetric configurations.
Yeah. Here
this
they
is
aggregate in the center
Exactly.
on top of each other.
right. Then you add, and then the
Then
picture
they
evolves.
start to bifurcate.
These symmetric configurations, like abricose lattices, they exactly geometry can be predicted. These configurations are known.
This
The way how the saddle configurations form.
no, it is dynamically. Here I have plotted it for very specific values of the angular momentum because these values correspond to the symmetric assignment. If this would be 4.2, for example, they would not be asymmetric anymore.
Sure.
And
I'm talking only about symmetric ones. Those ones can be predicted. So index formula does give a characteristic for them or not? Only for symmetric ones.
Index formula depends on the trajectory. But
so you cannot get this information from the index itself because index computes only can identify whether it's a saddle or.
If I take a saddle point, so I take a trajectory and then I look for the vector field at each point of the trajectory, and each point of the trajectory I have I take it here at each point of the trajectory I have a vector field. And if I continue this vector field, I can see if it's an internal tangency or an external tangency of the point.
Yeah, I understand. So this is for an individual object. This is why you take this difference between external and internal, and then add for the corresponding.
So that tells how that particular vector field behaves on the boundary of on that particular trajectory S1.
So
and that is this quantity. Then I can compute by computing this integral.
By higher D, by higher D, another question. By higher D,
higher dimensional.
Higher dimensional. Can you consider like strong topological insulators?
No, this is a two-dimensional.
No, this I know. But for higher D, do you see the analog?
No, I haven't.
Like in topology.
I cannot say, but I think that the Poincare index formula, because it computes the internal external trajectories, it's a trajectory specific. So you have to have a proper, then you have a proper clear surfaces, and you have to have I don't have a obvious. But as it stands, this is a two-dimensional quantity.
I mean, since you mentioned Kosterlitz-Thouless XY system, which has a relation to strong topological insulators, these configurations can be probably found on the surface of strong topological
insulators. That's a two-dimensional.
Exactly, on the surface you would observe this.
Yeah, so you could, but that could be some way to apply that, but I haven't. I cannot say anything.
I think it's interesting because I know people also look there for this anyonic configuration, symmetric configurations that you have.
But that's something I don't know about.
Yeah, thank you. Other questions?
No.
There is one more.
Thank you for the very nice talk. So the way I understand this is that this is quantum Hall. Like this is integer quantum Hall.
Pardon?
This is integer quantum Hall, essentially.
But why is this quantum Hall? I mean,
Because
I don't have
in-
magnetic field or anything like that. I had
Right.
just have a
But the statistical field that you have, the statistical
the
gauge field that you have, the parameter in front of it, if you parametrize it using quote unquote magnetic field, then that would be quantum Hall.
statistical field how it comes.
Yeah, it's a different context.
Yeah, the statistical field. This is just a mathematical statement. Is that if I have a parameter
You
times
see that
psi
phi there?
and another parameter
Yeah.
times x with gradient of psi,
Yeah.
then if I define this quantity, these two quantities are the same. It is just a
That's-
factor of the
That's the Landau gauge in the
yeah,
quantum
no, but
quantum
this
Hall.
is
But the
this is just a
phi,
mathematical identity. But yes, it could be in
It-
some
it
kind of
could
a
be.
Hall system. It
Yeah,
could be,
yeah.
yeah.
exactly.
Yeah.
But my question is, then the Poincare Index Formula tells you that when you tune these parameters and when you tune the angular momentum, you introduce a vortex.
Yeah,
When you introduce a saddle, you have to introduce a vortex.
yeah.
Yeah. And my question is, can you like tune or maybe pick some special values in which like you introduce two vortices at the same time? That would be like a fractional quantum Hall kind of scenario,
right.
but
I haven't looked into that.
okay. That would be interesting.
I'm in this case. I think it is that would my answer to that would be is that's an energetic statement. In these parameter values that I introduce, it is energetically an advantage to introduce one vortex. But sure, you could think that depends on dynamical details of the model.
Yeah. Okay. Thanks.
Okay. More questions? If not, then let's thank the speaker again.